Welcome to Talk Tensors. Today, we're doing a deep dive into a really interesting paper looking at how machines can get better at understanding emotional mimicry intensity, EMI for short.
Right, EMI. It's essentially how strongly we react or mirror an emotion we see someone else expressing.
And why does this matter for AI? Well, you can imagine, right? Virtual assistants that actually get the intensity of your reaction.
Exactly. Or robots that interact more naturally, more empathetically. It could even be useful for, say, mental health assessment, picking up on subtle cues.
But it's tricky. Capturing that sort of continuous, nuanced flow of emotion across different signals, face, voice, it's a real challenge.
It absolutely is. We're okay at basic emotion labels, but this intensity, this mimicry intensity, especially using multiple modalities like vision, audio, and text together, that's been tough.
So this paper we're looking at introduces a new framework to try and get around some of those limitations in estimating EMI.
Yeah, they call it a dual-stage cross-modal alignment framework. Bit of a mouthful, but the idea is pretty clever.
Yeah. It sounds technical, but it's about getting different data types, video, audio, the words being said to align their emotional meaning better in 2 steps.
And they've also got this temporal-aware dynamic fusion module.
Right, and a quality-guided modality fusion strategy. So basically, it looks at how emotions change over time and figures out which signal, face, voice, text is the most reliable at any point.
Which is important because real-world data isn't always perfect.
Definitely not. And the payoff seems pretty big. They're reporting a 40% improvement over the best previous methods on the Hume-VidMimic 2 dataset.
That's a significant jump. So yeah, let's unpack how they did it.
Okay, so summarizing the paper, what's the core approach?
Well, the main thing is this 2-stage training method. Stage 1 builds on CLIP, the OpenAI model, linking images and text.
Yeah, familiar with CLIP.
So they adapt that idea using contrastive learning, but they do it separately for vision and text, and then for audio and text.
Ah, okay, so it's like pre-alignment, teaching the system the basic emotional vocabulary for each pairing first.
Exactly. It's modality decoupled pre-training. Get the vision text link solid, get the audio text link solid before trying to juggle all 3.
Makes sense, like learning individual instruments before orchestrating. What's stage 2 then?
Stage 2 is where the temporal modeling and fusion happen. For video, they use Temporal Convolutional Networks, TCNs.
TCNs, they're good at seeing patterns over time and sequences, right? Not just static frames.
Precisely, capturing that macro evolution of facial expressions. And for audio, they use Gated Bi-directional LSTMs.
LSTMs are great for sequences like speech. Bidirectional means looking forwards and backwards in the audio.
Yep, to get better context, capturing those local acoustic dynamics.
And then they bring it all together, but not just simply mashing it up.
No, that's where the quality-guided modality fusion comes in. It learns to assign weights dynamically.
Weights? You mean like deciding how much to trust the video versus the audio versus the text at any given moment?
You got it.
Yeah.
If someone's face is obscured, maybe it relies more on the voice and text. It uses differentiable weight allocation to figure this out.
That sounds really practical. Okay, and this was tested on Hume-VidMimic 2 across several emotions.
Yeah, Hume-VidMimic 2. About 15,000 videos looking at 6 emotions. Admiration, amusement, determination, empathic pain, excitement, and joy.
And the headline result?
An average Pearson correlation coefficient of 0.35. That's the measure of how well their predictions matched the ground truth intensity.
0.35, and that's the figure representing that 40% improvement.
That's the one, compared to the previous state-of-the-art baseline.
Okay, let's dig a bit deeper into the paper's structure. The introduction obviously sets the scene.
Right. It talks about the importance of EMI for HEI, AI, mental health, the usual motivations. But critically, it pinpoints the problems with older methods.
Like analyzing modalities separately or just kind of crudely concatenating features.
Exactly. Underutilizing the synergy between modalities, not getting fine-grained semantic understanding across them, and importantly, not having smart fusion strategies that account for varying quality.
So they're saying we need better alignment and better fusion.
Precisely. And they lay out their 3 main contributions clearly. That dual-stage training paradigm using CLIP ideas, the quality-aware dynamic fusion, and their specific temporal feature extraction using TCNs and BIL-STMs.
And they mention the dataset and the big performance jump right up front. Sets the stage well.
Then there's the related work section. This is where they position themselves against existing research.
What's the evolution been like in this area?
They trace it from earlier multimodal methods, sometimes with static weighting, to more recent stuff focusing on cross-modal interaction, maybe using attention or contrastive loss.
Like MULT or similar transformer-based approaches.
Yeah, things like that. But they argue their dual-stage approach is better at handling potential conflicts or redundancy between modalities compared to single-stage alignment.
Okay. What about the temporal modeling aspect?
They review TCNs for visual, Wave2Vec 2.0 for audio, acknowledging their power but noting limitations, maybe fixed receptive fields in TCNs or Wave2Vec 2.0, not directly mapping foams to emotion intensity.
And positional encoding, like in transformers.
They mention it, but argues standard positional encodings don't really handle multimodal temporal alignment well, especially when modality quality varies. They bring up things like OMRPE, but point out shortcomings regarding quality awareness.
Which circles back to why they developed their quality-guided fusion.
Exactly. And their combo of TCN and LSTM with segment-wise pooling is presented as an improvement.
And the cross-modal alignment part of related work, they compare to CLIP directly.
They discuss CLIP, but note it's image text only. Also CLIP for audio text, often single stage, and things like Flamingo, which are powerful but computationally very heavy.
So their niche is this dual stage setup. Align pairs with text first, vision text, audio text, then do a trimodal joint optimization.
Right. They argue it gives enhanced consistency without the massive compute of something like Flamingo, and better initial alignment than single stage approaches.
Got it. Moving on to the method section, how do they actually process the data?
Okay, specifics. Visual dot, video sampled at 5 frames per second. They felt that was enough for motion dynamics. Features extracted using CLIP's VIT-V16.
VIT Vision Transformer, why that?
They liked its global attention mechanism for capturing overall facial patterns, the semantics,
Makes sense?
and audio, processed in 20 meets windows, aligned with the video frames. Features from Wave2Vec 2.0 chosen for its strong pre-training on speech, good for emotion cues.
And text, how did they get that?
Speech to text via whisper. They chose the large V3 turbo version, highlighting its robustness from multitask training.
Whisper's pretty powerful. And then feature extraction from the text.
BERT. To get those deep, context-aware semantic features from the transcriptions.
Okay, so solid pre-trained models for each modality. Then the framework itself. Stage 1, the contrastive alignment.
Yep. 2 parallel paths, both based on CLIP's architecture. One for vision text, one for audio text.
So for vision text, VIT encodes frames, average pooling over segments, BERT encodes text, then a contrastive loss.
Exactly. LV2TIC pulls related vision text pairs together in the embedding space, pushes unrelated ones apart. Same logic for audio text using Wave2Vec 2.0 and BERT, giving the last heat loss.
Stage 1 optimizes just those two losses together.
All right, LVTT plus LA2T just focuses on getting those pairwise alignments right.
Then stage 2, they freeze those encoders.
Correct. Freeze the feature extractors.
Yeah.
VAT, Wave2Vec 2.0, BERT. Now the focus shifts to temporal modeling and fusion. They add cross-modal mapping layers, simple MLPs, to project features.
And the temporal modeling happens here, TCN for visual.
Yes, TCN captures multi-scale temporal dependencies in the visual features.
And bi-directional LSTM for audio spectral temporal dynamics.
Right. Then these temporally processed features are projected to a shared space via MLPs and concatenated.
But they enhance these temporal features further.
Yeah, a bit more refinement. For visual, segment-wise average pooling on the TCN outputs helps smooth things out.
And audio.
A gated attention mechanism on the LSTM outputs. It actually looks at the difference between adjacent frame features to calculate attention weights, focusing on moments of change.
Interesting. Okay, now the really novel part, that quality-aware dynamic fusion.
So they have a dedicated module, just an MLP, actually, that assesses the quality of each modality, visual, audio, text, at each time step, outputting a quality score, QMA.
How does it learn what quality means? Is it supervised?
It's learned end-to-end as part of the overall regression task in stage 2. The model figures out what quality indicators help minimize the final prediction error.
Clever. So it gets these quality scores. Then what?
These scores go through a softmax normalization. That turns them into weights PUCE V, POTE, POTE AABE, that sum to 1 at each time step T.
So dynamic weights representing the relative importance or reliability of each modality.
Exactly. These weights are then used to combine the enhanced features from each modality into a single fused feature vector.
And that fused vector goes into the final predictor.
Yep, that weighted fused feature goes into a transformer encoder, which makes the final EMI prediction, EMIT.
And the training strategy recap. Stage 1 optimizes contrastive losses. Stage 2 freezes encoders and optimizes the regression task using mean-squared error loss.
That's the core of it.
Okay, onto the experiment section. We know the dataset was Hume-VidMimic 2.
Right, 15K videos, 6 emotions, intensity from 0 to 1. They detailed the train validation test splits, durations, sample counts. Standard stuff, but important for reproducibility.
Evaluation metric was the mean Pearson correlation.
Averaged across the 6 emotions, yes. That's the key number they report.
Did they mention optimization details like learning rates, schedulers?
They did. For the stage 1 contrastive pre-training, they use cosine annealing scheduling with warm restarts SGD optimizer. Helps find better minima.
And for stage 2 fine-tuning?
They used EMA exponential moving average smoothing on the model parameters. Often helps with generalization and stability.
Good details. So the results, how did the individual modalities perform on their own?
Significantly better than basic baselines. Their contrastive pre-training boosted the VIT visual model quite a bit, and their audio feature enhancement helped Wave2Vec 2.02. Table 2 showed these unimodal gains clearly.
So even before fusion, their feature extraction and alignment work was paying off.
Definitely. But the multimodal results in Table 3 were even more interesting.
What did they show?
Well, combining modalities consistently improved performance. Interestingly, audio plus text was a very strong pair, sometimes outperforming visual plus audio.
So language and voice tone together are really powerful cues for this task.
It seems that way. But the best results came from the full VIT plus Wave2Vec 2.0 plus BERT combination using their dynamic fusion.
That's the 0.35 correlation score.
Yes. It significantly outperformed all unimodal and bimodal combinations, really highlighting the benefit of integrating all three with their proposed fusion mechanism. They stressed the contribution of the text modality and the success of the dynamic fusion.
So the conclusion basically summarizes this. Dual stage training, quality-aware dynamic fusion, tighter alignment, better robustness, validated on Hume-VidMimic 2, 40% improvement.
Pretty much wraps it up. It's a solid contribution to EMI estimation.
It feels like a really well thought out architecture, addressing specific weaknesses in previous approaches.
Agreed. The focus on alignment first, then temporal modeling, then quality-based fusion seems logical and, based on the results, effective.
Okay, that brings us to our novel notions segment. Where could this kind of approach go next? I was thinking. This dual stage idea, aligning modalities first. Could it work for other complex multimodal tasks, like, say, understanding human activities?
Oh, interesting. Like someone cooking from a recipe.
Yeah.
You've got video, maybe speech, sounds of chopping, and the text recipe.
Exactly. Stage 1 could align visual objects, tomato, knife, with the text instructions. And maybe align the audio chop the tomato with the text and the visual action.
Yeah, you could adapt the contrastive losses for that. Maybe bring in object detectors or action classifiers in stage 1 for more specific grounding.
And then stage 2 handles the sequence. The TCN tracks the visual steps, LSTM tracks the audio instructions or sounds, and the quality fusion handles, I don't know, a blurry camera view or background noise.
It makes sense. The robot needs to know which instruction corresponds to which action, even if one sensor feed is temporarily bad. Could be really useful for robotics, automated assembly.
Following complex, multi-sensory instructions in the real world, that feels like a natural extension.
Definitely. Here's another angle. Those quality scores. What if we use them more directly?
How do you mean?
Could this system give feedback? Like, hey, I can't see your face very well right now. Could you adjust the camera? If the visual quality score of V is consistently low.
An interactive quality check. That would be useful, making the system more collaborative.
And taking it further, do these learned quality scores actually match up with how humans weigh different modalities when things get noisy?
You mean like run experiments, show people videos with, say, muffled audio or obscured faces, ask them how much they relied on each cue to judge the emotion?
And then see if their subjective weighting correlates with the model's learned at values.
That could be fascinating. You would tell us if the model's learned strategy for handling noisy data mirrors human perception, or maybe it finds different, perhaps even better, strategies.
Yeah, it bridges AI interpretability with human perceptual studies. Lots to explore there.
Absolutely. Some really thought-provoking possibilities branching off from this work.
Strong foundation.
Well, that's our deep dive for today. The core takeaway is this dual-stage, quality-aware approach really pushes the needle on accurately estimating emotional mimicry intensity.
That 40% improvement on Hume-VidMimic 2 speaks volumes about the effectiveness of their method for integrating multimodal signals over time.
Definitely check out the paper if you want the nitty-gritty details. Link is in the description.
It's worth the read.
And a final thought to leave you with. As AI gets better and better at understanding not just what we feel, but how strongly we feel it, especially in response to others, how might that change our relationship with technology and maybe even our understanding of emotional communication itself?
Deep question. Lots to ponder there.
Indeed. Join us next time on Talk Tensors for another exploration into machine learning research. Thanks for listening.